Section 5.4 Generalized inverse or G inverse of a matrix. Suppose we have a system of equation Ax equal to B. We know that if A is non-singular, then x equal to A inverse B is the only solution. The question that we want to ask here is, if A is not a non-singular matrix, that is, if it is a square matrix which is singular, or if it is some rectangular matrix, can we still have some analog of A inverse which will satisfy such a relation? Specifically, we require to find this. If A is a singular matrix or a rectangular matrix, meaning number of rows is not same as number of columns, then does there exist a matrix G such that whenever you give me any such system, that is, give me any B such that this is consistent, then G times B will be a solution. Now we cannot talk about the solution because there may not be unique solution, but at least it will give me a solution. So the idea is, given A, you should be able to compute G. Now whenever someone comes up with a B, G has already been computed once and for all. Now whenever someone gives you any B such that the system is consistent, GB will be a solution. And that is the question, whether there exists such a thing. And the answer turns out to be yes, there is. And any such G is called a generalized inverse or G inverse of the matrix A. Now here is a word of warning. In fact, I learned this from the second author of the book. I learned it from Bhima, who told me that he had done his PhD on obtaining G inverses, and he said that that was just unnecessary work because all the things that you really need to know about G inverses may be learned in just a single evening. There are lots of results that we created. The results are not useful at all. In this context, you should remember that there is an ultimate result. That is what everybody uses. And that result is the following. Suppose I have a matrix, a real matrix, M by N. M may be equal to N, may not be equal to N, just a general real matrix. Then for this, there is a matrix which typically people denote by A plus, which is of the order N by M, which has the following wonderful properties. Number one, if Ax equal to B is a consistent system, if it is consistent, then A this plus B is a solution. So whenever it is consistent, this is a solution. So clearly this is a G inverse according to our definition. Secondly, if there are infinitely many solutions, this will give you a very special solution. It will give you the minimum norm solution, which means out of all the solutions, the solution which has the smallest length, that is, norm of x is minimum subject to this condition. If it is inconsistent, then also it has some wonderful property. Then this same vector A plus times B is a least square solution, is a minimum norm least square solution. What does that mean? If it is inconsistent, you can never have any value of x for which equality holds, but this vector will bring the left hand side and the right hand side closest together, and if there are more than one such value of x for which this minimum is attained, then it will pick the minimum norm x for which it will happen. And finally, there is a third property which says, subject to these conditions, this A plus is uniquely determined by A. That is, there is exactly one matrix A plus for given any A matrix which will satisfy both these conditions. So A plus is unique for A. So it is very much like A inverse, and there are computational algorithms to find this. Such an A plus is called pseudo inverse or Moore-Penrose G inverse. Thus, all that you really need to understand in order to apply G inverses is only about this type of G inverses, its existence, computational technique, and these properties. That's all. Now, Indian mathematicians, mainly C.R. Rao and S.K. Mitra, they spent a lot of time trying to find different results about G inverses, but they fell short of discovering this particular thing, which was discovered later. And as a result, the Indian school feels somehow confusedly proud about G inverse in general and holds this thing in the light of scorn or skepticism, because that is not something that we discovered. And that is why many Indian books, like our Rao Bhim book here, they will talk a lot about those unnecessary results about G inverses. But you should remember that all those things are outdated in the sense they are all subsumed inside just this wonderfully beautiful object. However, in this video, we shall be following the book. So, theorem 5.4.1, it says call G a G inverse of a matrix A if whenever I give you any consistent system Ax equal to B, that is whenever I give you any B such that B belongs to column space of A, then the vector G times B is a solution. I am not claiming that this is unique. I said a G inverse. In fact, in most cases it is not unique. And observe that this is perfectly silent about 2 points. Number one, what happens if it is inconsistent? And number two, if there are infinitely many solutions of the consistent system, which solution do you get? This definition is much cruder than the pseudo-inverse thing that we mentioned. The definition, of course, does not make it clear whether G inverse exists or not. That is given by the next theorem, which says every matrix, square or non-square or whatever, has at least one G inverse. The proof is pretty simple. It starts by taking a matrix A, suppose it is M by N, and taking its rank factorization. So it is M by R and R by N, where R equal to rank of A. I say the proof is simple, but the concept of rank factorization itself is not simple. So let me quickly remind you what a rank factorization is. Here what I am doing is I am taking the columns of A, and they span a space, of course. What I do is I pick a basis of that column space of A and take a basis, and that basis vector I stack side by side, and that I call my matrix B. As a result, every vector here can be expressed as a linear combination of these vectors. So this is my A. So take up the first vector. So it's a linear combination of these two. So this times this plus the coefficient. So I am writing down the coefficients when I express this vector as a linear combination of these two. Now again, you can take the second vector, that is also a linear combination of these two. So you will have two more coefficients. I will write them here in this way, the third vector and the fourth vector. As a result, you get another matrix. So the way I have created it, it is 4 columns, and so there are got 4 numbers here, and that you call C. I have got 2 vectors here, which means the column space dimension is 2, that is rank is 2, R is 2. That is a rank factorization. So it basically says take a basis and express everything in terms of the basis. So I just want you to take a rank factorization, and when you take a rank factorization, this matrix by very definition is full column rank, and you can similarly check that this matrix has to be full row rank. Now, whenever you have a full column rank matrix, that is the columns are all linearly independent, you have a left inverse. That's the left inverse. By this I mean it's a matrix such that B minus L times B will be the identity matrix. Similarly, whenever a matrix is full row rank, then C times C minus R, that is the right inverse, will be an identity matrix. So for any full column rank matrix, you have a left inverse, and any full row rank matrix, you have a right inverse. I claim that if you take G in this way, C, right inverse of C times left inverse of B, then this matrix, which is of the order n by m, must satisfy the condition of a G inverse. To check this, we take any consistent system Ax equal to B. I said it is consistent, so there is at least one solution to it. Suppose x naught is one solution. So B is actually equal to Ax, which is B C x naught. So GB, which we have to check that it is a solution, is C right inverse left inverse this. Now the left inverse is attacking B from the left, so they just cancel each other off, and you are left with just C right inverse C x naught. Now we cannot cancel these things off because the right inverse is occurring to the left. Now we have to check whether GB is a solution to Ax equal to B, that is whether this is equal to B. So let me do that. BC, that is A, and this is C right inverse C x naught. Now the right inverse comes to the right of this C, so they cancel off, and you are left with BC x naught, which is Ax naught, which is B as required. So this shows that any matrix has a G inverse. Now there's a little catch here. I started by saying that here is a matrix A, take its rank inverse. I take its rank factorization. The question is, does every matrix have a rank factorization? The way I gave rank factorization was just pick up a basis for the column space of A. Now, can you always pick up a basis? Well, there is only one vector space for which you cannot pick up at least one column in the basis, and that is when the vector space is just the trivial vector space consisting of only zeros. Then you cannot, here the size of the basis is 0, you cannot make a matrix out of it. And that will happen if all the columns of A are 0. So this argument works for every non-zero matrix. But fortunately, if A is the 0 matrix, then also G inverse exists, and it is pretty easy to prove, because now you have to take any consistent system. Now when will this be consistent? If this is 0, it will be consistent only when B is also 0. And in that case, you need one solution. As long as the right hand side is 0, you know that x equal to 0 is always one solution. So you can take G equal to also the 0 matrix. So if this is m by n, you just take this n by m so that you can multiply B with it, and that will be 1 G inverse. And the book naughtily asks you a question, what are the other G inverses? And you should think about that. It has a very simple answer. Now this theorem is one of the many theorems that give various characterizations of G inverses. So suppose A and G are two matrices. Now for all these things to make sense, we need m by n and this to be n by m. G is a G inverse of A. I say TFAE. TFAE means the following are equivalent. That is, if any one of these four conditions hold, then the other three must also hold. So the first condition is G is a G inverse of A. If and only if AGA is equal to A, if and only if AG is idempotent and rank of AG equal to rank of A. If you do not know what idempotent means that its square is itself. So this term idempotent means, so a matrix B is called idempotent if B square is equal to B. So in this case, AG is idempotent means AG is equal to AG again. and similarly for GA. Now, the proof is not very difficult, but somewhat confusing, and we proceed in the following way. So, in this case, G is the G inverse of A according to our definition. So, I will consider this system AX equal to A1, where A1 is the first column of A. There is no doubt that this is a consistent system because this definitely is in the column space of A. In fact, it is a column of A. So, one solution of this will be given by G times A1 because it's a G inverse. So, I have A times this must be equal to A1. I put this in place of the solution. Now, of course, the same thing holds even if I work with A2, even if I work with A2, 3, for all the different columns, so I can write for all I. So, if I stack them side by side, then I have this result. AG, I stack them side by side, A1, AN. Remember, when I multiply like this, AG multiplies this, then AG multiplies the next one in this way. That will be equal to A1, AN. And that is A. So, AGA equals A. That proves 1 implies 2. To prove the converse, that 2 implies 1, I have to start with a consistent system. Suppose Ax equal to B is consistent. And I have to show that G times B, this G that satisfies this condition, is a solution. Now, I say it is a consistent system, so it has got at least one solution. Suppose X naught is one such solution, so B is Ax naught for some X naught. Now, I have to check that G B is a solution. That is, I have to check that A times this must give me B. Okay, let's check. B I already know is Ax naught, so it is AG Ax naught. AGA is equal to A, so it is Ax naught, and Ax naught is B. So, I do have A times GB is B, so GB is a solution of this consistent system, and according to my definition, that means G must be a G inverse of A. Now, I want to show if 2 implies 3, so I have AGA equal to A, and I want to check if AG is idempotent. That means AG times AG, whether that is again equal to AG. Of course, it is AGA is nothing but A, associativity. I can multiply these things first, so it is A and G remains. So, AG is equal to AG, so it is definitely idempotent. Now, about this, rank of AG equal to rank of A. For this, we have to remember a very important result. If I take any two matrices BC and form their product, that is, two matrices for which the product is defined, then rank of BC must be less than or equal to both rank of B as well as rank of C. When you multiply two matrices, rank can never go up, and that is obvious because rank means the dimension of the column space or the row space, and when you are multiplying matrices, you are taking linear combinations. By taking linear combinations of vectors in a space, you can never get anything outside that space. You can get only things that are inside. So, the rank can never go up. Now, let's just use this fact here, and you will immediately see that rank of AG must be less than or equal to rank of A, because AG is obtained by multiplying A by something. Now, I also know that A happens to be AGA. So, rank of A is same as rank of AGA. And what is AGA? AGA is AG times something. So, this must be less than equal to rank of AG. So, rank of A is both less than or equal to rank of AG and also greater than equal to rank of AG. That forces rank of AG to be equal to rank of A. So, we have finished proving 2 implies 3, and by the same kind of argument, you also get that 2 implies 4. All that remains to be proved is 3 implies 2, because if that can be done, then 4 implies 2 is also very similar. Now, The proof that is given in the book is the typical Rao Bhim Shankaram ugly version here. I will give the same argument but in the following way. So I have got 3, which means AG is an idempotent matrix. So AG is AG. What I want to show is AGA is A. So if only I could cancel off this G from the right, I would be done. The only problem is I do not know whether G may be cancelled like this. Well, it is here that this fact comes to our rescue. You observe that this space, column space of AG, must be a subspace of column space of A. That is always the case, because what is AG? AG is obtained by, the columns of AG are obtained by taking linear combinations of the columns of A where the coefficients come from G. Now, this result says that their dimensions are also the same. So here is a subspace whose dimension is same as that of the full space, which means I must have equality. If that is the case, I might as well say this. Column space of A is a subspace of column space of AG, because anything is a subspace of itself. And as a result, I can write that all the columns of A can be thought of as linear combinations of columns of AG. So A must be of the form AG times sum C. So C gives you the coefficients when you want to express the columns of A as linear combinations of columns of AG. Well, once you get such a C, that solves your problem. You post multiply both sides by that C. Now AGC is A and this AGC is also A, so you are left with AGA is equal to A, and that is precisely what you needed. So this completes the proof, and I will end this video here because it is getting long.